Hello and welcome to this video on solving radical equations containing one radical. Alright, so in this video I just have several examples of radical equations involving one radical, right? So one expression in a square root or one expression in a cube root, etc. And we'll go about, solving those equations, figuring out what values I can replace the variable with to make a true statement, right? That's what it means to solve anything, any equation. And I'll also point out the steps I'm following, and I will be following the same steps every single time. So let's begin. So my first example, I'm asked to solve. I have again an equation with one radical. The square root of 3x plus 1 underneath that radical, then minus 4 equals 0. Alright, so again, just a single radical. And off to the side, I will write down the steps I'll be following for this first example. And the steps I'll be following for this first example are exactly the same steps I'll be following for every subsequent example. Alright, so the first thing is I would like to isolate the radical. Right, get the radical term on its own side, and you may notice that this is very similar to how we solved, absolute value equations, and it's really going to be similar to how you solve any equation with a special symbol in it. First, you want to get it alone. Okay, so this expression here, this term, this square root, this radical, I would like to, isolate this first, get that on its own side. So it's already on the left, just might as well keep it on the left. In order to do that, isolate it, I would need to get rid of this negative 4. Alright, so I'm going to be adding 4 to both sides. Alright, so that'll give me the following. I have the square root of the 3x plus 1 on the left equals, and then 0 plus 4 on the right, or just 4. Alright, the next step, after isolating the radical, step 2 is I would like to then undo the radical, get rid of it, just like with again absolute value equations, or you're going to see any equation with a special symbol. Very often you're going to isolate that special symbol and then get rid of it somehow. Now the way to do that is to remember that when you take an nth root, and I'll write the little property over here, and raise it to the nth power, the root and the power basically undo one another. If you go through and use that product property for radicals, you'll see that they'll basically disappear. All right. So what I'm going to do is raise both sides. Oops, R-A-I-S-E. Right. I'm going to raise both sides to the index power, right? To the index power. And just recall that you have this property of radicals. Right? In order for this step to mean anything, recall that if you were to have, if you have the nth root of some expression a, and you raise this to the nth power, on the outside like this, right? Again, as long as this is a real number, right? If this is an even root of a negative, this isn't going to apply. But the nth root of a to the nth power, that nth root and nth power here basically kind of just undo each other, and you're left with the radicand. So you see, get rid of the radical symbol. So you just pay attention to the index. Raise both sides to the this is the index of the radical here in this little v area. Raise both sides, raise to a power that is equal to the index. Okay. So in doing this, I'm going to take, this entire left side and raise it to the second power, right? Remember, this is a square root, so the index is 2. So I'm going to raise both sides to the second power. Same thing for this entire side here, which again is just the number 4. I'm going to raise that to an exponent of 2. All right. Now the performing of this step again will get rid of the radical symbol basically. All right. So we have the square root of 3x plus 1 squared. That'll just be the radicand. 3x plus 1 equals, and then 4 to the second, 4 times 4, 4 squared is 16. And then I solve the resulting equation, and of course, check your solutions. Right, so step 3, solve the resulting equation. Because after I get rid of the radical symbol, it should be some polynomial equation. As you see here, this is a linear equation, a first degree equation. And then of course the last step is to check your solutions in the original equation. All right. Right, the reason I say this, right, I'm going to actually be checking these. It's because this act of raising both sides to the index power, like here I'm raising both sides to the second, and then getting rid of the radical. The act of doing that actually changes the domain of the problem, the domain of the expressions in the equation. Because remember, when you take an even root, you can only take an even root of a non-negative number and have the result be real. So earlier in the problem, 3x plus 1, that can't be negative. But when you square both sides and then change it to this 3x plus 1 equals 16, now there's no radical, and the value of x could be anything. Right? It doesn't matter if it's positive, the 3x plus 1 is positive or negative or not. So what happens when you raise both sides to the index is you may be changing the domain of the problem. So you might actually invite in what are called extraneous solutions, right? And those are numbers that you think are solutions, but when you go back to the original equation, they do not work. All right, so we'll definitely have to check because of step 2. All right, it's because of step 2 that we really need to check our solutions in the end. Alright, so continuing on with this, I'd subtract 1 from both sides, giving me 3x on the left equals 15 on the right, and then divide both sides by positive 3. And we're getting, again, a possible solution of x equals positive 5. Right? But please, especially when I'm raising both sides to some power, definitely check this result. Do not just automatically assume it works, that it is a good solution. So I'll do that on the next page. Right? So what was the original equation? I'll write it down again. Well, I'm not going to write it down. I'll just write what it's going to look like when I plug 5 in. All right. So I'm going to plug 5 into the original equation. So we have the square root of 3 times, and then not x, but I'm going to replace x with 5, and then plus 1 in the radicand. And then after that, minus 4. Is that equal to 0? And let's see if this ends up being a true statement. Alright, so 3 times 5 plus 1, that's 16. So we have the square root of 16 minus 4 equals 0. And please don't forget, I've mentioned this many times in other videos if you've been watching mine. When you see a radical symbol, right, with an even root. So a square root, a fourth root, a sixth root, etc. You're being asked for, that symbol means give me the non-negative square root or non-negative even root of the radicand. Because yeah, I know that negative 4 to the second power, right, negative 4 times negative 4 is positive 16, great. There is a negative square root of 16, that's negative 4. But again, when you see this symbol, you're asked for the non-negative square root. So the square root of 16, or the non-negative, the principal square root of 16 is 4. And, is 4 minus 4 equal to 0? Yes, that's 0 equals 0. That is a true statement. So I'm going to actually put this up here in a circle, a box. That works. All right, that is a good solution to my equation. It does make it true. Great. And you might see some texts where they write off to the side. They might write the solution set to this equation is the set, right? Little curly braces here. The set with the number 5 in it, right? The only solution to this equation is the real number 5, right? So you might see texts where they write the solutions like that as a set of numbers that actually make the equation true. Okay. So go through the steps one more time. Right, I'm going to follow these same steps every single example I do when I'm solving a radical equation. Isolate a radical and basically remove that radical by, raising both sides to the index power, right, whatever the index of that radical was. And again, be careful, right? This step here may cause an issue later. When you raise both sides to a power, the domain of the expressions in the equation may change, like it did in here. For the domain of this expression is totally different than the domain of this expression. And then solve the resulting equation. Of course, because of step 2, you must check your solutions back in the original equation, as you might come across some of those extraneous solutions. So please be careful and be diligent about checking your work. Wonderful. All right, so again, keep those steps in mind. I'm going to be doing the same steps every single time. All right, so my next example in solving the following equation with a single radical, the square root of 2x plus 35, and then afterwards minus 2 is equal to 3. What value of x or values of x make this a true statement? So step 1 was I would like to isolate the radical. All right, in order to do so, I need to get rid of this, this negative 2 term then. So I'm going to add 2 to both sides. That'll leave me with this equation. The square root of 2x plus 35 is equal to, 5, positive 5. All right, then comes the part where I undo the radical. Raise both sides to the index power. Again, this is a square root, so the index is 2. All right, so I take this entire side, raise it to the second. This entire side, which is just the number 5, raise it to the second power. And then on the left side, you have the square root of something, and then raise outside to the second power. That'll just undo the radical, leaving me with 2 times x plus 35, leaving me with the radicand of that radical. And that's equal to, 5 to the second. 5 times 5 is 25. Then we, after undoing the radical, solve the resulting equation, right? So here I would, subtract 35 from both sides, giving me 2x on the left equals, and then 25 minus 35 is negative 10 on the right. Then I would divide both sides by positive 2, leaving me with x on the left equals negative 5 on the right. Again, please don't just automatically circle this. Right? We're going to check this. All right, off to the side here. So put a little bar here. We're going to check our solution. So let's see. Back in the original equation, I have the square root of 2 times x, but I'm checking -5 for x, so 2 times -5, and then plus 35. And we have -2 afterwards. Is that equal to 3? All right. Now the radicand, 2 times -5 is -10. -10 plus 35 is 25, right? So we have the square root of 25, then -2, is equal to 3. Again, remember this is the non-negative square root of 25, so it's just positive 5. And is 5 minus 2 equal to 3? Yes, indeed. You have 3 equals 3 here. So again, I have a very good solution. Right? I'll go back and you can circle this or write out that solution set stuff that I did in the first example that you might see in some books. So the solution set is simply the set with the number -5 in it. Wonderful. Okay. So I have, again, several of these. Most of them are square roots, but I do have a few ones with cube roots at the end. And if you ever see a 4th root or a 5th root, you would do the same thing, but just be raising both sides to, the 4th power or the 5th power. It all depends on the index. Alright, so here we go again. I have the next example, the square root of 2x plus 3, and then, sorry about this thick plus sign, but that's plus 8 equals 6. Alright, let's see what happens again here. Alright, so following the same steps every time. Got a single radical, so I'd like to isolate that radical term. Alright, so I'm going to get this square root of 2x plus 3 alone by getting rid of this positive 8, right? So I'm going to subtract 8 from both sides, leaving me with the following equation, right? The square root of 2x plus 3 is equal to, 6 minus 8 is -2, right? Now, remember what I've been saying in every single example. When you see this symbol, the square root symbol, 4th root, 6th root, any even root symbol, radical symbol, when you're taking the even radical of some radicand, remember the result is the non-negative square root. But this on this side is a negative number. So this side is a non-negative number, right? When you see the symbol, that means it is the non-negative square root. So on the left side, I have a non-negative number, the non-negative root of something, being equal, and then the right side is a negative number. This cannot happen. All right? You cannot have a non-negative number be equal to a negative number. So if you see that, this can't happen. All right? So that means that this equation has no solution. All right? So the equation has no solution. You can write that out in words. You can write that out in words like this, or very often, again, you see the solution set written out in books sometimes for equations. You might just see an empty set of braces, which I have brought up in prior videos. This is this empty set of braces, the set with nothing in it, referred to as the empty set. Another way to represent the empty set is with like a circle with a slash through it, almost like a no smoking sign. So again, either one of these might also be written when you have no solution to an equation. All right, just nothing is a solution, the set with nothing in it. Okay, so hopefully you would recognize that. If you isolate if you have an even radical on one side and a negative number on the other, that can't happen. But let's say for some reason I didn't recognize that. All right, so again, this is going to be correct here. There's no solution to this equation. Like I said, let's say we didn't see that. Okay, so let's say we had, our square root of 2x plus 3 on the one side equals, and then the negative 2 on the other. And then I decided to go through the steps. If I didn't see, there's no solution here. If I didn't see that, we'd follow the usual steps, right? I isolated the radical, and then I want to undo the radical. Right, so I'm raising both sides to the index power, right? That's index of 2, so I'm raising both sides to the second power. And on the left side, right, that radical is undone. So we have 2x, just 2x plus 3 equals, and then negative 2, squared, that's negative 2 times negative 2, that's positive 4. And then we solve the resulting equation, right? I would subtract 3 from both sides, right, giving me 2x on the left equals 1 on the right, and then divide both sides by positive 2, and that would give me x on the left, and 1/2 on the right. And you might think, hey, earlier you said there was no solution, but here I'm seeing x equals 1/2. Well, you got to check it. Right, you have to check it back in the original equation. Does it actually make the original equation a true statement? So let's do that off to the side here. I'm replacing x with 1/2, and this was our original equation. Right? So I have the square root of 2 times x, right? So 2 times 1/2. Right, replacing x with 1/2, and then plus 3 on the inside. And then outside that we have plus 8. Is that equal to 6? All right, let's see. Well, 2 times 1/2, right? The 2 in the numerator, 2 in the denominator, common factor would divide out, cancel, leaving me with 1. So this is 1/2 of 2, plus 3 is 4. So the radicand is 4. I have the square root of 4, plus 8 equals 6. And don't forget, I've been saying this a lot. When you see an even root, this is the non-negative square root of 4. So not plus or minus 2 or minus 2, but just the plus 2, just positive 2 for the square root of 4 when you see that symbol. And plus 8. Is 2 plus 8 equal to 6? Well, no, it's not. Right? 10. You get 10 equals 6. This is a false statement, right? So no. That's bad, right? So no, this is not a solution. I put a big X through it, right? And what I mentioned earlier, that this 1/2, this would be called an extraneous solution. Right, a solution that you get when you go through and solve something, but doesn't actually end up working in the original statement, the original equation. It's called an extraneous, or sometimes I've seen it written as a superfluous, just unnecessary solution. Doesn't work. So again, all the solutions I found didn't work, didn't make it true. So the equation has no solution. Let me go back to here. The solution set would be this empty set. Okay? So yeah, so like I mentioned earlier, right, that raising both sides to the index power, right, raising both sides to some power might actually change the domain of the expressions in the equation, and you might, be inviting in some of these extraneous solutions. So please, 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 I can't emphasize this enough. Check your solutions when solving a radical equation. Okay, another example. Here I'm asked to solve the square root of 2x plus 1 equals, and on the other side, x minus 1. Alright, so this is already set up the way I want. See where the radical is on its own side. There's nothing added to it, nothing subtracted from it, nothing multiplied or divided, nothing it's multiplying or dividing by. It's already alone. I guess the only major difference between this example and the previous several examples is now this other side has two terms, and one of those is a variable. Right? So far in my other examples, when I isolated the radical, there was just a number on the other side, right? Not a variable expression like I have here. All right, so the radical is already isolated. Great, step one is done. Then I would like to undo the radical by raising both sides, right? So the entire, let me actually write this again. Sorry, I shouldn't mess with the original equation. So here's the equation again. Square root of 2x plus 1 equals x minus 1. And I'm going to raise both sides to the index power, right? The index of this radical is again 2. So I'm squaring this side, which will undo the radical. And then I'm squaring, again, this entire side. All right, so you got to be really careful with this. The left side is just going to be the radicand, the radical and the power basically undo one another. And I'll have 2x plus 1 equals, and this other side, don't forget what it means to square something. Right? When I tell you I'm taking x minus 1 and squaring it, don't distribute powers, please. Right? You cannot distribute powers over sums or differences. What it means to square something is to actually take that base, take that side, x minus 1, and multiply it by itself. So it means do x minus 1 times x minus 1 and do all the distributing, or the foiling if you want to call it that. So I distribute the x, right? That would give me x squared. That would give me, the x squared minus x, and then I'm done with the x, I move to the negative 1. There's another minus x, right? There was minus x from these two and minus x from these two, so that'll be minus 2x. And then negative 1 times negative 1, positive 1. So please don't just make this x squared minus 1. Do not distribute powers. Remember what it means to square. You're taking that whole side and multiplying it by itself and doing all the distributing and combining like terms. Great. So after raising both sides to the index power, I have this nice polynomial equation that is now a quadratic equation, right? There's a degree 2 polynomial over here. All right, and hopefully you recall I put up it's been a while now, but a past video about solving polynomial equations by factoring. A good way to start solving a polynomial equation where the degree is higher than 1, right, like a degree 2 here, is to take everything to one side and 0 on the other. So what I'm going to do for this one, I'm going to take everything to the right. I like having a positive lead coefficient. I like having that positive 1x squared. So I take away everything from this side. I'm going to take away the 2x and take away the 1. And don't forget to do it to the other side. All right. And then the left side is now nothing, 0. On the right side, we have the x squared. We have minus 2x, would be minus 4x when combining those. And then positive 1 plus negative 1, that's 0. So I take everything to one side, 0 on the other, and then we factor this polynomial. 0 equals, and then these two terms have the greatest common factor of x. And if you want to, please look up other videos of mine on factoring polynomials, or look up other videos from other people, or look in your books on factoring quadratic polynomials or factoring polynomials. Please do. I'm not going to get into all that here. This is mostly about solving radical equations. So I factor out the common factor of x times, and then the remaining factor would be x minus 4. And then what I have here is a product with two factors, right? X times x minus 4. A product equal to 0. Okay, and by that 0 product property, if a product of two numbers is equal to 0, then one of those numbers must be 0, one or the other. So either x equals 0, or the other factor, x minus 4, equals 0. And we solve these. So either x is 0 or x is 4, right? For this equation, I would simply add 4 to the other side. All right. Now notice again, I am not going to be circling these. I'm not saying they're any good yet, because as always with these radical equations, I've raised both sides to a power that might have changed the domain of my problem, the domain of the expressions in my equation, so I must check the solutions. So here we go. I'm going to do that on this page here. So the original equation was, this guy up here, right? The square root of 2x plus 1 equals x minus 1. So first I'll check when x equals 0. So we have the square root of 2 times 0 plus 1, and is that equal to x minus 1 or 0 minus 1, right? Again, just replacing x with 0 back in the original equation. Alright, so this radical, the radicand underneath is 0 plus 1, that's just 1. So is the square root of 1 equal to 0 minus 1 is negative 1. Now remember, when you see this symbol, I say this a bunch, when you see this symbol, it means the non-negative square root of 1. So what's that? The non-negative square root of 1 is simply 1, right? Just positive 1. That is not negative. And is 1 equal to negative 1? No, it is not, right? So this isn't giving me anything good, right? So 0 is one of those extraneous solutions. So back on this, that's extraneous. That is not a good solution. I'll cross it off. All right. Now let me check the other possible solution I got from this quadratic equation here, positive 4. All right. So I'm going to check x equals 4. And again, back in the original equation, we have the square root of 2 times 4 plus 1. And is that equal to 4 minus 1? Right, replacing all the x's with 4. Alright, well, look at what's this radicand here? 2 times 4 is 8, plus 1 is 9, so I have the square root of 9 equals, and then 4 minus 1 is 3. Is this true? Yes. Remember, again, this is the non-negative square root of 9, so positive 3, and I get positive 3 equals positive 3. Totally a true statement. So 4 works. 4 is a good solution. So after all that, all right, I'm going to put that in a little circle. The only solution to my original equation is 4 for x. And again, you could write a little solution set equals and then the set with just the number 4 in it. But please don't forget to check your solutions. Wonderful. Alright, so all those examples had square roots, right? A single expression inside a square root. My last two examples will involve, a little higher indexed root, cube root. So this example, I have the cube root of 3x plus 1 then afterwards minus 4 equals, negative 6. I'm following the same steps every single time with these equations with a single radical. I'm going to take this radical term. I wish to first isolate this. All right. So the first thing I'll do is, do the addition of 4 to both sides. That gets rid of that negative 4, leaving me with the following, right? The cube root of 3x plus 1 on the left equals, and then negative 6 plus 4 is negative 2 on the right. Now I had an example up earlier in the video where there was a square root equal to a negative, equal to a negative. And remember, that had no solution, because when you see the square root symbol, that's representing a non-negative number. But when you have an odd root, right, cube root, fifth root, seventh root, etc., when you have an odd root, right, odd roots can be any real number. Can be positive, negative, 0, whatever. So this, so far, is looking okay. Alright, so I've isolated the radical, and then again I raise both sides to the index. So that's the third power here to undo the radical symbol. So I cube this side, raise it to the third, and cube this side. Right. So on the left, I have, just the radicand now, 3x plus 1 equals, and on the right, negative 2 times, remember, a negative number to an odd power will be negative, and negative 2 times negative 2 times negative 2 is negative 8, right? Then we subtract 1 from both sides, gives me 3x on the left, equals negative 9 on the right. And we divide both sides by positive 3. So x on the left equals, negative divided by positive is negative, and then 9 over 3 is 3. Right. But as always with these radical equations, don't just circle that, don't just automatically assume it's good. I'll tell you right now though, because these are odd roots, remember the radicand can be any real number, and the output can be any real number. So the domain of the original expression, x can be any real number, and even after I take both sides and raise it to the third power, this expression here, x can be any real number. So the domain didn't change when I raised both sides to the index power. So there's a good chance that I don't have extraneous solutions here, but still it's a good habit to check. Please check always when we're solving these radical equations. So there's only one number to check, negative 3. So back up here I've got the cube root of 3 times negative 3 for x, and then plus 1. Then we have minus 4 afterwards, equals, and then negative 6. Alright, so what's the radicand here? 3 times negative 3 is negative 9, plus 1 is negative 8. Right, so I got the cube root of negative 8, then minus 4. Is that equal to negative 6? And negative 8 is one of those perfect cubes, right? The cube root of negative 8 is negative 2, right? We saw earlier negative 2 cubed is negative 8. So that's negative 2, and minus 4, is that equal to negative 6? And yes, it is. Negative 2 minus 4 is indeed negative 6. So you get the statement, negative 6 equals negative 6. That is true. So yes, indeed, negative 3 is a good solution to this equation. Makes it true. Great. And notice again, I followed the same steps as I did with the square roots, right? Nothing changed. So I've got just one more here, and this last example is kind of just a refresher as to the relationship between these radicals and rational exponents. All right, so you might look at this and say, hey, this isn't a radical equation, right? We have the base on this exponent of 1/3, you have the quantity 2x minus 3. all of that raised to the 1/3 power, right, a fraction power. Then minus 7 afterwards, is equal to -4. And again, you might think, hey, remember, this isn't, this isn't a radical. I'm not seeing the radical symbol. Off to the side, I'm just going to remind you, right, I've put this up in past videos if you've been watching, that when you see a number or a base raised to a fraction power, like 1 over n, like this, a to the 1 over n power, that's exactly the same. It means exactly the same thing as taking the nth root, right? So the denominator of the power is like the index of the radical. And then the base underneath that power is going to be the radicand. Right? So if you remember this, then anytime you see an equation where there are variables raised to fraction powers, it really is like a radical equation. In fact, I'm going to change this to its equivalent, radical form, where there's an actual radical symbol. So that would be the following. This base 2x minus 3 is raised to the 1/3 power, so that's the same thing as the cube root of 2x minus 3. Right, so that's the cube or index of 3, right? The denominator of the power is the index of the radical of, and then the radicand is the base, 2x minus 3. And then we have minus 7 after, equals -4. And then now it's no different than the one I had, the last several examples I've done this whole video. Right, first I would like to isolate the radical. So I'll be doing that by adding 7 to both sides, leaving me with the radical on the left, right, the cube root of 2x minus 3 on the left, equals, and then -4 plus 7, +3 on the right. Once the radical is isolated, I raise both sides to the index power, right? Raise both sides to the 3rd power. And that undoes the radical on the left side, leaving me with the radicand, right? The 2x minus 3 equals, and then on this side, 3 to the 3rd power is +27, right? 3 times 3 times 3. And hopefully you can see here, I'm not going to write the steps this time. This is the last one. I'm just going to, if I were to add 3, I'd have 30, right? 27 plus 3, 30 over here, and then I would divide by 2. And 30 divided by 2 is 15. Right? So the possible solution to this equation is 15. Right? So I'm going to check this. Remember, back in the original equation. So I'll do that again over here. Let's separate this, do the checking over here. Now I'll keep it to the again, go back to the original, and just remember that the 1/3 power is the cube root of the base, right? So I have in parentheses 2 times 15, right? 15, 2 times 15 minus 3 in parentheses, that number being raised to the 1/3 power, or taking the cube root of that. Then minus 7, is that equal to -4? All right, so simplify what's in parentheses first, right? The base here, 2 times 15 is 30. 30 minus 3 is 27. So this whole thing is just 27 to the 1/3 power, and then minus 7. Is this equal to -4? And remember, this 27 to the 1/3 power is just what's the cube root of 27, and that's 3. So I have 3 minus 7, is that equal to -4? Yeah, 3 minus 7 is -4. We end up with the statement -4 equals -4. Yes, 15 is the solution to this equation. Does make it true. All right, so to recap, when you see an equation with a single radical, isolate the radical, step 1. Step 2, raise both sides to the index power the index of that radical as an exponent. That'll undo the radical, get rid of it. And step 3 is, after you've gotten rid of the radical, solve the resulting equation. And then, step 4, and always check your solutions back in the original statement, right, the way it originally looked. See if it's a true statement, because you might come across some extraneous solutions. So please, 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 I can't say this enough, check your solutions always. Great. And as I always like to say at the end of these videos, do the best you can to try to learn the material on your own before you go out looking for help. I found that when people take the time and the effort to learn something on their own, they tend to remember it better and for longer, and are more proud of themselves for it. So of course, read the material, read through the author's examples, perhaps even try to work out solutions to some of the author's examples before you see how the author did it, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously, work on tons of exercises, practice problems, check solutions to those if they're made available so you can see how you're doing and track your progress. And don't just give up on a problem after one attempt or two attempts. Very often there are several approaches that'll work for any particular math problem. So if after several attempts at a problem you're still not getting how to do it, perhaps you should go back and read the material again, maybe even a third time. Because if you've been working on some problems, chances are you have a good idea as to what the author wants from you, right? What the author is asking from you. So when you go back and read that second or third time, you'll know better what to look out for in the reading. Some things might pop out at you that didn't the first time through, and it'll make working on the problems that much easier. But if after that, if after several read-throughs of the material and several attempts at problems, you're still not understanding, still not getting it, it's not a sign of weakness whatsoever to go out looking for help, ask for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos online. There's tons of those too. Videos like this one, or plenty of other ones out there better than this one. I assure you they're out there, and you can find them easily. But just keep at it. Stay persistent. Keep practicing. Don't give up. And above all, and I think this is the hardest thing, but also the most important, is to believe in yourself. Stay positive about the subject, even through your struggles and failures. Because when you struggle and fail, those are the greatest learning opportunities, the greatest learning moments, when you are able to learn from your failures and learn through your struggles, learn from your mistakes. So just believe that you can do it. Believe that you can make it through, and maybe even make a game out of it. Make it, try to have fun with it. So stay persistent, keep practicing, stay positive, and don't give up. And I just know you'll get it. And thank you very much for watching.